Hi, PCalc, it's Mr. Szybisty, and today we're going to talk about section 3.3, which is related rates. Now, in section 3.3, there are actually two other topics. There is optimization and concavity and the second derivative test. You're going to want to make sure that you read about concavity and the second derivative test in the book. We'll talk about it in class, but it's not something we're going to talk about in this video. Let's get started talking about some of the general processes for solving a related rates problem. Related rates can sometimes be the most difficult type of problem you're asked to solve in calculus. It's a problem where you're asked about one rate when something else is going on. Like, for example, if you're blowing up a balloon, the volume is changing at a certain rate, but so is the radius of that balloon, and they're related somehow through some equation. You might have a sphere that's growing or shrinking like a melting snowball. The radius is shrinking, and so is the volume, but they're shrinking at different rates. Or we're filling up a cone, or we're dumping a bunch of sand into a cone-shaped pile. The height's changing, the radius of that cone is changing, and the volume of that cone is changing, and they're all changing at different rates. So the first thing that you would need to do is identify that what you've got is a related rates problem. It's going to ask about some rate when some condition is happening, or it's going to actually specifically say rate and then when some particular condition is happening. That's when you know you have a related rates problem. Oftentimes that's one of the toughest things to do, is to be able to identify, I'm going to need to use this sort of procedure. Now this is where the general procedure gets kind of fuzzy. A related rates problem is one of the vaguest types out there. You're going to be asked to do this sort of related rates problem where something is changing when something else is changing in so many different scenarios. What I want to do is give you sort of the basics. Every related rates problem is going to boil down to these few things. And then we'll focus on how do they apply in the different settings, because in each different setting it looks different. And probably on the AP exam it's going to look like something we've never thought of. So the next thing we do is draw a picture if that's possible, and most of the time it is. That picture is crucial to understand what's going on and the relationship between variables. Then write an equation that uses the variables in the picture. That could be a formula for area. That could be the Pythagorean theorem. That could be something that has to do with a volume equation, and the equation might be given to you in the problem. 3, form your inventory. We'll talk about what that looks like later, but pretty much it's listing out, writing out, what do you know from the problem and what are you looking for? What's going to answer the question? The fourth is we're going to put our equation into motion through differentiation. We're going to take a derivative of it. And when we do that, our independent variable is going to be time. And so you're going to see a lot of implicit differentiation here. If you take a derivative of a y, you'll see a dy dt. If you take a derivative of a v, you'll see dv dt. If you take a derivative of an a, you'll see dA dt. What you'll see in almost all of these is a dt in the denominator. The rate has to do something with time in almost every situation. And then finally, we're going to substitute the information that you know about and then answer the question. So let's jump in. We've got 3 examples to talk about. Here we are, example 1. We're making a snowman, so we start to form a spherical snowball for the head. At the instant at which the radius is 3 centimeters, the radius is increasing at a rate of 10 centimeters per minute. At what rate is the volume of the ball of snow changing at that instant? So I can already know, and I can already tell you that this is a related rates problem. Looking at that final sentence, at what rate is the volume changing at that instant? So at the instant when the radius of the ball is 3 centimeters. So let me draw a picture. Here's my snowball. And I know from geometry that this has got a center and it has a radius, and that volume equals 4/3 pi r cubed, and that is my formula for the volume of the sphere. Notice what this does is it writes an equation that uses all the variables in the problem. The variables in the problem, we were talking about radius and volume, and this is an equation that has radius and volume. So now let's form an inventory. The inventory is going to be a place where I can store all of the information that I learned in this problem. So let's list it out. Radius is 3 centimeters. So r equals 3. Radius is increasing at a rate of 10 centimeters per minute. So a rate is a derivative. dr dt equals 10. Notice again, my independent variable is a t, so it is the rate at which the radius is changing as time is changing, and that's the 10. Now finally, what are we looking for? The rate, the volume of the ball of snow is changing, so that would be dv dt. That's what I don't know. Now let's go through and actually put this in motion. Our next step is going to be differentiating this equation right here. Then we'll plug things in and then solve for what we want to find out, the dv dt. Our next step is to put this equation into motion, and that's through taking the derivative of both sides. Derivative of v is dv dt, and then the derivative of this, it's power rule, so the 3 is going to come down. It cancels with that 3, so this would be 4 pi r squared. I took the derivative of an r, so implicit differentiation says we have to add this on the outside, dr dt. Now we can start to plug in everything we know. We don't know dv dt. From my inventory, I realize that's what I want to find out. So then I have 4 pi, and then r, which is 3 squared, times dr dt, which is 10. So I know that dv dt is equal to 360 pi, and they would probably ask us for units. The units of volume in this problem would be centimeters cubed, and the units for time would be seconds. And there's my final answer. At the instant when the radius is 3, and as long as that radius is increasing at a rate of 10 centimeters per... I'm sorry, this is minutes, isn't it? Per minute. Those would be our units. All right, let's take a look at the next example. An 18-foot ladder is propped up against a solid wall. The base of the ladder begins to move away from the wall at a rate of 0.2 feet per second. When the base of the ladder is 7 feet from the wall, how fast is the top of the ladder falling? So I could draw this. Here's my wall right here. And I know that I have a ladder propped up on it, and I know that this is going to be an 18-foot ladder. No matter how it moves, I know it's going to be 18 feet. And so I'm going to put a couple different measurements here. I'm going to put the length that it is away from the wall. I'm going to call that length x, and the height of the ladder at any time is y. Now I know that I've got a very, very good equation for this, and this is Pythagorean theorem. I know that this is a right angle. So I know that x squared plus y squared is equal to 18 squared. So x squared plus y squared is equal to 324. Now let me form my inventory. The base of the ladder begins to move away from the wall. So this is the base of the ladder moves away from the wall at a rate of 0.2 feet per second. So that is dx dt. And I know from this is 0.2. Let's see, what else do we know? When the base of the ladder is 7 feet from the wall. So this is going to be when x is equal to 7. How fast is the top of the ladder falling? I want to know dy dt. That's what I'm looking for. And I check one more time to make sure that I've got all the information in my inventory, and I do in fact have all the information that they gave me. So from this, I should be able to figure out what dy dt is. Alright, the next thing I'm going to do is take a derivative of both sides. Put this model into motion. 2x, and I just took a derivative of an x, so implicit differentiation says dx dt, plus 2y dy dt equals 0. And now I start to plug in everything I know. I know that x is 7. I know that dx dt is 0.2. And then 2. And now I have to figure out what y is. And I'm looking for dy dt, so that's not an issue that I don't know what that is. But I'm looking for the y. I need to figure out what y is when x is 7. And I think back to my right triangle, 18, 7, and y. I want to know what the y is when the x is 7. Well, I can use Pythagorean theorem to figure that out. 18 squared minus 7 squared is going to be 275, and the square root of 275 is 5 square root 11. So I know that I can now put this into my equation here, 5 square root 11. Just doing a little bit of simplification, this is 2.8, that's a 2, plus 10 square root 11 dy dt equals 0. And then solving for dy dt would give me 10 square root 11. Nope, I'm sorry, that's not going to be right. We'll have negative 2.8 divided by 10 square root of 11, which is approximately negative 0.0844. And now we would need units, and this would be feet per second. And this makes sense because my ladder is falling down, and so it would make sense that it's falling at a negative rate. All right, we've got one more example to do. This one talks about pouring gasoline into a cylinder. Example 3. Gasoline is pouring into a cylindrical tank of radius 3 feet. When the depth of the gasoline is 4 feet, the depth is increasing at 0.2 feet per second. How fast is the volume of gasoline changing at that instant? So let me start by drawing a picture. Here's my cylinder. And I know that it's going to have a height and a radius. So I'm going to go through and I'm going to write an equation that talks about all of these. I've got depth, I'm going to have a radius, and I'm going to have a depth or a height. My formula is volume equals pi r squared h. And now I start to form my inventory. So I know that r is equal to 3. I also know that my radius is never going to change no matter what happens in this problem. So dr dt is equal to 0 because the radius will never change. It will stay constant. Now the height, at the instant that I'm curious about, is 4 feet. And it's changing at a rate of 0.2 feet per second. Finally, I'm looking at how is the volume changing. That's what I'm going to be looking for in my problem. So now let's go through and let's actually take the derivative and put this model in motion. Alright, now as I go to take the derivative of this, I know that the derivative of v is dv dt. But then I start moving in and I realize I'm going to need product rule because I'm multiplying two variables together, the r and the h. So I'll pull the pi outside and worry about it later. Derivative of the first times the second. Don't forget the dr dt because I just took the derivative with respect to r, or with respect to t of r, plus keep the first, derivative of the second times dh dt. That goes back to the implicit differentiation. I took a derivative of an h. Now I can start plugging in what I know. dv dt is what I'm looking for. And so that's equal to pi times 2 times the r, which is 3 in my inventory. The h is 4. dr dt, remember the radius is never changing in this problem, so this is a 0. Plus radius squared, so this would be 3 squared, times dh dt, and from the inventory I know that that's 0.2. Going through and doing some simplification, I can now tell you that dv dt is equal to pi times 9 times 0.2. So dv dt is equal to 1.8 pi. And now I would probably need to include some sort of units. Volume would be feet cubed, and time is seconds. So there's my answer for that. Now you'll notice that we just had 3 very, very different examples, and the way that we attacked them in each of them were very, very different. On the AP exam, you might be given something like this. You might be given the equation and you're talking about the rates. The process is the exact same. Draw a picture, write an equation, write down what you know in an inventory and what you're looking for, differentiate, take the derivative of both sides, and it's probably going to be with respect to time. You'll see dv dt's, dr dt's, dh dt's, all that sort of stuff. Make sure you don't forget things like the product rule when you need to use them. After you take the derivative, substitute in, and then you can solve for what you know. Make sure you write down what questions you have. This is a confusing topic. Let me know what made sense and what didn't make sense. Bring it into class and we'll talk about it. And I'll see you guys later.